In part 6, we're working with an exponential function. The domain of an exponential function is all real numbers. There's nothing that you can put in for x that will give you an error message. The range, on the other hand, we'll have to think about based on transformations. The range of the normal exponential function, so if I have g of x equal 2 to the x, and again the base doesn't matter here, any base at all, if g of x is 2 to the x, then the range is only positive numbers. In other words, you can only have outputs from an exponential function that are greater than 0. So that also means that there's a horizontal asymptote at y equals 0. Now, in the function that we have, we are taking the normal 2 to the x function, scaling the y-coordinates by 3, but scaling the y-coordinates is not going to make the asymptote be anything other than y equals 0. But then we're subtracting 2 from all the y-coordinates. Well, if before we had a horizontal asymptote at y equals 0, then when we subtract 2 from all the y-coordinates, our new horizontal asymptote will be at y equals -2. And if you draw a picture of this graph, you should see the graph having a horizontal asymptote at y equals -2. So that means the range of this function is -2 to infinity rather than 0 to infinity. So what you should know is that for the regular exponential function, the domain is all real numbers, and the range is only the positive numbers. And then any exponential function, other exponential function, we can figure out its domain and range by thinking about transformations of that function. Average rate of change, this is just again to remind you that this is an important concept. This is something you'll see a lot in the beginning of a calculus course. So it's really just the slope between 2 points on the curve. And so we only really have to be able to evaluate the function. F of 2 here will be 10, and f of -1 is going to be -1/2. And in the denominator I have 2 minus -1, so that's +3. So in the numerator I have 10½ basically, which is 21/2, divided by 3, which is 7/2. As a reduced fraction. In part 7, we're trying to find missing sides and angles in various triangles. This is another case where I won't do every part of every problem. I'll try to just do a variety of parts so that you can make sure you're doing the right thing. We know in this first right triangle that if we have 2 of the 3 sides, then the third side is going to come from the Pythagorean theorem. So if you use the Pythagorean theorem on this, you'll find that 5 squared plus 12 squared equals 13 squared. So the missing side there is 5. The missing angles, theta would be one of them. We're going to find missing angles by doing inverse trig functions. So if I use the inverse tangent, for example, and since I have all 3 sides here, I could use any of the inverse trig functions. But the tangent of theta is 12/5, and so the inverse tangent of 12/5 must be theta. If you put this in a calculator, and my calculator is on degree mode, so I'll just stick with that, then I get an angle of approximately 67.4 degrees. So that'll be the angle theta. But in a right triangle, the other angle, of course, is complementary, so this extra angle should be 90 degrees minus 67.4 degrees, which is approximately 22.6 degrees. In the second right triangle, we have an angle and a side, so that means that we automatically know the other angle. Again, this is the complementary angle, so we know that up here is 20 degrees. So that's an easy angle to add. The sides I'll be able to add by thinking about trig functions. So if this side, I label this side A, then we know that the sine of 70 degrees is A over 12. And so with a little bit of one algebra step and using the calculator for the sine of 70 degrees, I find that A has to be 11.3. And then similarly, if I'm trying to find b, I would use the cosine of 70 degrees, and I'll get b is approximately 4.1. So in this problem, there's no instructions for how to round these things, so I'm just rounding them off to just the same decimal place everywhere on the test. If I ask you for a certain number of decimal places, then that's what you should stick with. In the two triangles below, we have three sides given but no angles, and so we have to use the law of cosines. Remember, the law of sines is really only useful if we know most of the angles, and in this case we know none of the angles. So law of cosines is definitely our only option here. These are not right triangles, so we don't have the option to use the Pythagorean theorem or the methods we used in the previous problem. So let's pick an angle in one of these triangles, and we'll do the calculation for one, and I'll just write the answers for the other. The law of cosine says that the opposite side to that angle, we're focusing on the angle theta, so the opposite side is 8. 8 squared is 6 squared plus 7 squared, just like the Pythagorean theorem says, except this is not a right triangle, so we know that's not right. So that's how we know we're supposed to adjust. And the law of cosines adjusts that value by 2 times the product of the sides, 6 times 7, times the cosine of theta. So if I take that calculation and get my cosine of theta by itself on one side, so work out all these numbers, we actually get that cosine of theta needs to be 1/4. And my calculator's still in degree mode, so when I ask for the inverse cosine of 1/4 to the nearest tenth of a degree, what do I get? 75.5 degrees. So the angle that was called theta here is 75.5 degrees. If I do the same kind of calculation for the other two angles, I'll get this angle is 57.9 degrees roughly, and the other angle is 46.6 degrees. Now in the second triangle, this is an isosceles triangle, and so I find that I actually have a lot less work to do, because once I know one of these angles, I'll actually be able to fill in all of them. So I'll pick this one, call this one theta, and again, my law of cosine says that the opposite side, 6 squared, is the sum of the squares of the other two sides minus the adjustment term So if I start with that equation, then I can solve for cosine of theta, and I'll get cosine of theta is 1/3. And so then again I use the inverse cosine button on my calculator, and I find that theta is roughly 70.5 degrees. So the nice thing about that is that since this is an isosceles triangle, not only is theta 70.5, but this angle has to also be 70.5. And if you look at the calculation you would have to do using the law of cosines, you'll see that it's exactly the same computation, so it makes sense that it would be the same thing. And then of course the three angles have to add up to 180, and so I know over here this angle is roughly 39 degrees. Now if I wanted each of those to be more accurate, I would want to do the calculation out to more decimal places, but the point is that with an isosceles triangle, once you find one angle, then really you can fill in all of them. So it's a little bit less work for that kind of problem. The last problem is sort of the prototypical law of cosines problem. We only have one missing side, so we'll call this C. And the law of cosines says that C squared is the sum of the two squares of the sides, just like the Pythagorean theorem, but then we have to correct 2 times 6 times 10 times, and I'm running out of room, cosine of 45 degrees. So the number on the right is just a numerical calculation, so we can just use a calculator to figure out that C squared is 51.15, and so that means that C is the square root of that, so C will be approximately 7.15. Now the angles in this triangle, we have a choice. We can use the law of sines or the law of cosines because we do have one angle, so it's not quite as bad as the case before, but we certainly could do it that way. If you do want to use the law of sines to find an angle, you should only apply the law of sines to the smallest angle in the triangle. In other words, never use the law of sines to find the largest angle in the triangle, because the law of sines is incapable of returning a value that's bigger than 90 degrees, and there's always a chance that the biggest angle in your triangle is bigger than 90 degrees. So let's let me label this angle capital B, and we'll find B using the law of sines. If you did want to use the law of cosines, just do it like the two middle problems where we did that each time. So the law of sines says that the sine of B divided by 6 has to be the same thing as the sine of 45 degrees divided by 7.15. So the law of sines relates the sine of an angle to the length of its opposite side, and it says all these things have to be the same. So once we have that equation, then it's just a matter of solving for sine of B. So we'd say sine of B is approximately, we'd have to use a calculator, sine of B is approximately 0.59, which means that B in degrees is approximately 36.4 degrees. So the angle B here, down in this corner, is 36.4 degrees, and then we can use the fact that the three angles have to add up to 180 to find this largest angle. If you want to just try it, try finding both of those angles using the law of cosines like we did in the problems above, and see if you get the same answer.